Right. The next talk is faster inverse maintenance for faster conic programming by Shunhua. Jiang.
Okay. Let's see. Hello, everyone. My name. Wait. So my name is Shunhua. I'm a fifth-year PhD student at Columbia, and I'm also a Simons Fellow for this semester. Today, I'm going to talk about faster inverse maintenance data structure for faster conic programming problems. And I should mention, if you are interested in my talk today, please also check out the videos of a lecture that I gave last week in the bootcamp about matrix data structures, where I will cover a lot of the stuff that I talk about today in more details. Okay, so let me first start from a bigger picture about this recent progress on trying to use better data structures to achieve faster optimization algorithms. So many algorithms for optimization problems are iterative in nature, for example, gradient descent or taking Newton steps. And all these algorithms, high levelly, you can always measure their time as the number of iterations times the cost per iteration. So when designing these algorithms, there are always two themes. The first one is to reduce the number of iterations, and there has been extensive studies on that. And the second part is what I will focus on today, which is to reduce the cost per iteration. And the idea behind this is that many iterative methods are very robust inherently. So instead of computing the variables from scratch in each iteration, which can be very expensive, we can use data structures to implicitly maintain some solution and only do a smaller update in each iteration. And sort of what I will talk about today is about my research, which is focused on using inverse maintenance data structure for the type of algorithms that's interior point methods and for conic programming. So next, let me define these three definitions here, and then I will give you some list about recent progress, about other people's work and my work as well. Okay, so let's start with the definition of conic programming. So in conic programming, what we wanted to do is we wanted to optimize some linear objective subject to some linear constraints, and with the extra hard constraint, which is the variables should be in some convex cone. The simplest and most well-known example is linear programming that Bento just talked about, where in this example, our cone is the non-negative orthant, as shown in the figure here. But there are also other examples. Another very widely used example is semidefinite programming, where in this example, the cone is the cone of positive semidefinite matrices. And you can see the cone here in the figure on the right, where this is the cone of PSD matrices that have size 2 by 2. And there are also other examples. Another example I will cover today is sum of squares optimization, where in this problem, the cone is the set of polynomials that can be written as a sum of squares. And there are also other examples. Okay, now we've talked about conic programming. Let's move on to the other two definitions that I have in the first slide, which are inverse maintenance and interior point methods. So one of the most widely used algorithm for conic programming is called interior point method. This method is not only fast in theory, but it's also very fast in practice. So it's implemented in many solvers. And high-levelly, what does it do is that this is an iterative algorithm that moves in the interior of the feasible region and gradually moves towards the optimal solution. And each step of the IPM can be viewed as a Newton step. So you can view it as Hessian inverse times the gradient. And now you see where the inverse shows up. And the observation is that in IPM, the Hessian is usually changing pretty slowly. So we can use a inverse maintenance data structure that only perform some update to your inverse and maintain this inverse during different iterations. So this data structure will support two operations. The first one is an update operation where we only change a few entries of the matrix itself. And the second operation is a query operation that will output the matrix vector product of the inverse of Hessian times some vector. And we can design better data structures, and then by using a better trade-off between the update and query, this will improve the cost per iteration. And I should mention this is a very old idea that dates back to the original paper by Marker in 1984 and by Vadia in 1989. But there has been recent new interest in this big framework, and there has been more complicated amortization scheme and better data structures that gives improvement. Okay, so next I will talk about some recent developments starting from LP. So for LP, the formulation that we consider the general formulation that I talked about conic programming would become this formulation here, where the constraint is just that the x are all non-zero, are non-negative. And then we have some constraint matrix here, A, which have size d by n. So there are usually two cases that we consider for LP. The first one is the square case, where you have about the same number of constraints as the number of variables. And the second one is the flat case, where the number of constraints is much smaller than the number of variables. Okay, and then we start from some old paper by Vadia that I mentioned on the previous slide as well, where he showed that, another thing I should mention, all the results that I cover in this slide on the next slide will just ignore the bit dependence, because they will all have this L dependence that Benho just talked about. So they all fall into the other category that he said. Yeah, okay. So let me start with this paper by Vadia, where he showed that they can, by using this slowly changing framework, you can get root n iterations is standard, but you can get n squared cost per iteration, where if you compute the hash and inverse naively, it would take n cubed if you're in practice, or n to the omega, where omega is the fast matrix multiplication time if you are in theory. Okay. And then there has been recent work on both two sides. Let me just quickly mention on the side of reducing the number of iterations, there's a seminal paper by Lee and Sidford, which get root d iterations, and they use a different barrier function. So they change the IPM itself. And on the side of reduce the cost per iteration, all the recent work sort of follows on trying to answer this broad question: can we solve linear programs in the optimal time? But what does that mean by optimal time? Well, number one, in order to solve an LP, you need to solve some linear constraints. So as a lower bound, it's the time of solving linear equations. And as another lower bound is you have to read your input matrix. So your input sparsity would be the optimal time. And there has been, for solving linear systems for general dense matrix, we don't know anything better, but then just compute the inverse itself, which would take n to the omega time, where omega is the matrix multiplication exponent. And let me show some results here. So for the square case, this paper by Cohen, Li, and Song in 2019 showed that for LP, we can recover the same running time as the current matrix multiplication time, where they gave a runtime of n to the omega plus n to the 2n 1/6. And the later improvement by myself and other collaborators show that we can further improve this n to the 2n 1/6 to decrease it to n to the 2n 1/18. I talked about this in more details in the lecture last week, so you can check out the video if you're interested. And then on the flat LP case, the current best running time runs in order nd plus d to the 2.5. So if you have your variable size is more than d to the 1.5, then this already gives the same running time as the input size. Okay, and you can see like there's, let me just quickly mention like a straightforward open problem would be, so this is the input size time when your input matrix is dense. What if your input matrix is sparse? Is there any way to exploit that? I think that's unknown right now. Okay, and second, let me go through other conic programming, which start at SDP and SOS. So for SDP, our formulation would be, we still have the linear objective and a bunch of linear constraints, but now they're with respect to the matrix X, because our variable is the X that is a PSD matrix. And in this case, we usually say there are m number of constraints, and m should be smaller than n squared, because otherwise you have more number of constraints in your variables, and some of them become trivial. Okay, so the classic result for SDP is by Nesterov and Nemirovsky in 1992, where for SDP there's also root n number of iterations, and their cost per iteration is m squared n squared plus m times n to the omega plus m to the omega. And then there has been research recently follow about reducing the cost per iteration for SDP. So one paper in 2020 showed that you can improve the cost per iteration to m n squared plus m omega plus n omega. And a later paper by myself and other collaborators, we show that in some regime, we can further improve upon this previous paper. So in the case where there are many number of constraints that have roughly the same order as the number of variables, we get a similar result as in the LP case, which would run in like into the omega time for the current matrix multiplication exponent. And we can also use the same framework to reduce the running time for sum of squares optimization as well. Okay, so finally, let me end up with one very specific open problem that I'm happy to explore when I'm here, which is, can we further improve the running time for SDP solvers? Because if you look at the running time of the current two state-of-the-art LP solvers, I don't think they are tight right now. So I think there's still room of improvement. And another question would be, can we get a better iteration count for SDP solvers as well? Because for the LP solver, as I mentioned, there was this recent paper where it reduces the cost, like the number of iterations from root N to root D. And in some cases, you can have much fewer number of constraints than the number of variables. So it's unknown if we can get something similar for SDP or for other conic programming questions. Okay, so that is all. Thank you.
Yep. Has there been work on bounding the space requirements for solving these things?
I don't think so, but I also don't think they use that much space. I think it's a space usage is like, correct me if I'm wrong, someone in the audience. I think it's.
I'm wondering if you can get sub-quadratic, leaving aside the input.
Oh, that's a good question, but I don't think there's any work on that. Like, not that I'm aware of. Yeah.
Yeah, because for example, something I did long ago with first order methods on certain SDPs, certain specific SDPs, you can actually do that and actually use them in the approximation algorithms for which you are using the LPs in time linear. So if you have a matrix, for example, that's sparse, you might want to do it in space that's number of non-zeros.
There are works that exploit other structures, but if they're sparse, it would imply that. For example, I think there are works that exploit if your SDP, some graph corresponds to the SDP, has low tree width, I think it will have some like linear running time. For those special SDPs, it's probably in the same direction as what you're saying.
Sushant and I were just exchanging glances. I don't think we know how to solve linear systems subquadratically.
Yeah. Basically,
Space.
Is there
subquadratic space?
Is there any hope of solving linear systems in subquadratically?
I don't have a good story for hope, but I haven't.
I mean,
But I haven't thought about it. So
Yeah.
Anybody?
I don't want to take away from the speaker. It's an interesting discussion.
Any other questions? Maybe I'll ask a question. So some of these recent breakthroughs on max flow go by increasing the number of iterations by doing
Yes.
something simpler. Is there any hope for doing that for richer classes of LPs? Or
Yeah, I
when
think
all of
that's
these
a
were on square root
very
in-
interesting question. So we are currently trying to remove the 1/18, and that's one idea we are trying to exploit right now. So yeah.
Okay. Any other questions? All right. Well, thank you again.